All right, so here we are. This is going to be a long lecture. It's in fact so long that I can't even guarantee after looking through the slides over and over again that I have properly proofread it. So we'll see what happens. If you notice a conspicuous edit in the middle, it's because I fell asleep on the keyboard and had to pick things up tomorrow. So what I want to talk about is the gzip format, and most importantly, what's going to take up the vast majority of this lecture is this scheme called Deflate, which is nominally independent of gzip. It is the only scheme legitimately supported by gzip, and so they sort of go hand in hand. But Deflate bitstreams can show up in other contexts. So Deflate is a more general scheme than just gzip files. It shows up, for example, inside of PNG images. It's also used in the zip file format, which is nominally an archive and container format as well. So what we want to talk about is, first, if I generate a file with gzip, I certainly have to know things. So if I do this, I certainly have to know things like how is the deflate bitstream sort of nested inside that file. And then we have to talk about what is the deflate bitstream. And there is a lot of stuff to cover. And it is, if you remember the earlier lecture on the Unix compress tool, it's sort of like that. A lot of it is pretty, I don't know, boring minutia, but we have to get through all of it, and it is a significant detail overload. And what's really frustrating, and one reason why I developed that gzstat tool that is part of assignment 2, and I'll post a separate video demonstrating that, is that it can be very frustrating with all of those details floating around to actually have to implement your code and make it work basically all the way through before you can test it. Because if you don't do every single thing and get everything closed off, write the entire bitstream in a way where all the headers are in place, the decompressor just rejects it and you don't know why. So I've written a utility provided with the assignment that tries to give you some debugging information. But we have a long way to go before we know quite what's going on. So I created a text file. This slide is showing this. I've created a text file like I did in the compressed lecture. In this case, I think it's this example, which we've used over and over again. I am making sure to look at a hex dump of my input file because, as we know, we can't assume that putting text in a file means that what we put there is the only thing in the file. For example, I showed off earlier in the course that it's very common if I used Vim or something to create the file that it's going to stick in a new line, which is 0x0a, at the end whether I want to or not. And you can turn that off in your vimrc file, but people generally don't do that. Usually it's good to have that in there. So it's good before we begin debugging compression tools to make sure that we actually know what we're looking at. So here I have an input file. I run it through gzip with no settings. You might notice that in previous lectures I usually use gzip-9, which forces the highest performance mode. It used to be that you might not do that because it would use too much CPU, but we've got tons of CPU time these days. But gzip by default, I think it defaults to -5 or -6 or something. And then we run through, I'm using standard input and standard output like you will use on the assignment. But like the compress tool, there are other ways of using it, but we'll use it this way. We create this file. We usually use the extension .gz for the encoded file. And then we take a look at it. And we'll notice that, interestingly, on this input, we actually end up with a larger compressed file. And so what I want to talk about is, first, what does it mean to put anything into this .gz format? And then we'll discover that, for example, just like the compressed format, there is a magic number. There is a bunch of metadata that we don't really care too much about. We have to know how to put it there, though. That's important. In assignment 2, you've actually been provided with a template that does the initial metadata for you. And then at the end, so somewhere in here is a deflate bitstream, probably starting somewhere around here. There is a deflate bitstream. And then at the end, the last 8 bytes, so that would be this stuff, comprise a combination of a checksum to validate that the data that was decompressed when you decompress it is correct, and the total number of compressed bytes encoded in a 4-byte, a 32-bit value. So the gzip format's a bit heavier weight than the compress format, and that's for a lot of different reasons. And inside of the gzip container, there is this deflate bitstream, which is itself a sort of container because each deflate block has its own little headers and things. And we have to talk about all of that somehow before the end of this lecture. And I'm now 5 minutes in and we're on slide 2, so we're off to a good start. Hopefully we finish the lecture sometime before the assignment is due. So we want to talk about the gzip format, but I want to be very clear that really most of this is on the deflate bitstream, which is nested in there somewhere. And really that's because .gz is just a container. It is a way of describing a chunk of compressed data so that it can be decompressed and that it can be, we can validate it that it's error-free, and to some extent that we can understand aspects of how it was compressed, not just the scheme used, but the modification time, what operating system was used, which theoretically can be helpful, although many of those metadata aspects are ignored these days. So one of them, which is interesting, is that the .gz format by itself, so you might be familiar with seeing archives of type .tar.gz. The .gz format by itself is actually capable of holding multiple distinct compressed files, so you don't actually need to use an archive before you compress it. But for a variety of reasons, we don't usually do that. These days, we use gzip to encode one file. So we do something like this. If I want to encode a whole bunch of files or a bunch of directories, I make it a tar file or something similar. Usually we use tar. And then I compress that one single archive. And that's the main reason is that the tar format is much more flexible and better at capturing all the different details of files than gzip by itself. Another thing that's very interesting is that the gzip container, one of these, I think it's this one, the third byte in is actually a flag that says what compression method is being used. Theoretically, gzip actually supports apparently some variety of different compression methods, even though for whatever reason the actual gzip decompressor will complain if you use any method but deflate. If you take a look at the gzstat code, so gzstat's a utility, like I said a minute ago, that I will discuss in a separate video. If you take a look at the code, you will discover that deflate is option 8. So that's why that byte is 08. Deflate is encoding scheme number 8. The other ones are encoding scheme 0 is uncompressed data, which deflate also supports an option for that. There is an option for LZW. Compressed mode 1 is LZW, the Unix compressed style LZW. Option 2 is a format called PAC, which is an ancient format that predates the Unix compressed tool. Option 3 is something called LZH, which is some member of the LZ family. Options 4 through 7 don't mean anything for some reason, and option 8 is deflate. And it turns out the gzip decompressor refuses to take anything but option 8. So strangely, this turns out to be a strange orphaned option. And it turns out that the gzip format has evolved such that basically you sort of have to, it assumes everything is in deflate format. So the only format we can use, just in case you're planning loopholes for the assignment, the only format we can use is the deflate format. So we have to learn it. There's no way around it. And the deflate bitstream, which is nestled in there somewhere, that's a different bitstream description. They evolved in tandem, but they actually are two separate things. One is a bitstream sitting inside this gzip container. And assignment 2, which by the time you watch this has been posted, is all about writing a good compressor for files in this format. And it's significant. Assignment 1 was writing a compressor for files in the old compressed format. Now suddenly it's important to talk about good versus bad, because you're actually provided as the starter code on assignment 2 with a completely standard compliant compressor. It just doesn't do any compression. It just dumps the data uncompressed back into the gzip file, which therefore makes it does produce valid output that can be decompressed. So the goal is pivoted to attempting to achieve some quantitative compression advantage as opposed to just doing something in a particular format. So the overall structure of a .gz file is this. So just, it running from beginning to end, it looks like this, where the very last thing is that element called isize. The standard for what the format contains, so what constitutes a valid .gz file, is defined in this document called RFC 1952. Usually these days we're familiar with, we have the IEEE standards like IEEE 754, which is the floating point numbers. We've got these international standards organizations that develop internet standards or collectively standardize various things. Gzip is standard in the sense that everybody agrees what the format should be, but the standard itself is this weird document RFC 1952, which is this arcane old-fashioned, like sort of the old internet way of people proposing new protocols. So RFC stands for request for comment. And you can look this up. I'm sure there's a great Wikipedia article describing these strange documents. So this series of documents, the RFCs, they're numbered. They contain all sorts of weird stuff, including weird, irrelevant, like April Fool's jokes. There's a famous one about specifying a modification to the HTTP protocol for if your device is a teapot or something. RFC stands for request for comment, and what it amounted to was you would develop some new document that described something, and then you'd send it to this sort of mailing list with a request for comment. So comment on this new proposal. And many of these documents formed because they were written relatively formally and they described something. They basically became de facto standards. And so that's where we're living these days. We are spending assignment 2 implementing this thing that isn't even described by the proper kind of standard. It's described by this weird informal thing that's sort of been baked in over time. Everybody knows what RFC 9052 is. There's one canonical document that describes the format. But even it was never formally accepted by some standards body. Now, that said, because it's not a real standards document in the official sense, it's a much more pleasant read. I actually found implementing the gzip format, I basically only had that document and the source code for the gzip compressor as a reference point. That was a great deal more pleasant than, for example, my adventures implementing the JPEG format, with the JPEG's incredibly anal retentive written standards document from a real standards organization, where you're just paging through, chapter after chapter, defining terms, and they never want to use the terms that anybody else uses because they define everything like lawyers. RFC 952 is a bit of a breezy read, and I actually encourage you to take a look at the RFCs for this assignment. Probably you'll spend more time with RFC 1951, which is the one for Deflate. The RFC 1952 is just for the gzip container. So the way a gzip file is supposed to work is that you have this header, which describes the overall format of the file, and then you have a bunch of compressed blocks, and then you have this footer. And these days, gzip files look like that. They're just one combination of these three things. Theoretically, it's actually possible for inside of a single .gz file there to be multiple instances of this entire package, each of which would be called a member. And that is how you would be allowed to compress multiple files using the .gz format as sort of an archiving format. That is, you could play with that a bit, but we're not going to worry about that. We're going to use gzip. We're going to write a gzip compressor for the modern use of gzip, which is one file. If we want to compress multiple files, we'll make an archive ourselves beforehand. So formally, all of these three sections together form what's called a gzip member. And we will assume in our assignment we're only going to have one member in the file. As I said, play around with it, but just to be clear, if you write something that generates multiple members, not only will it not help you, it'll probably throw off our automation, and so you won't get any benefit from it either. So assuming we only, it said should only contain, I guess we should be careful. If we're talking about standards language, better say must. Should doesn't mean the same thing as must. So if you're going to generate only one of these things, then this thing here truly is a header. It is the beginning of the file and it appears only there, and this is the end of the file and it appears only there. And all of the action is happening inside of this set of compressed blocks. And we'll notice later, you could, if you wanted to, take a 1 gigabyte file and encode it into one massive compressed block in some cases. So the blocks are deflate bit streams. They are separate deflate bit streams. So we'll get to that hopefully sometime before the end of this course. Before that, though, we have to talk about the header. So the header has to contain all of these fields. If you glance over RFC 1952, you will notice that there's actually a whole ton of optional fields you can add. And we don't care because we want to optimize file size for one thing, and also because those optional fields don't really help us with compression. They're generally just metadata that is irrelevant to our purposes. In some cases, it's gratuitous metadata. So one optional field you can add is an arbitrary text comment, which is interesting because I'll give a small exercise in a couple of weeks that deals with that, but otherwise it doesn't help with compression. It just allows you to fold in extra data that nobody else sees. So before we talk about how the header, like what the bytes are, I want to talk about laying down some ground rules. One advantage that we have is, we remember from the compress tool, there was this really odd way that the bits got turned into bytes. And we're still going to have that problem here because we're going to work with bits that aren't in bytes. But we'll define it once and we will use it the whole way through. So it is consistent between gzip and deflate. And also keep in mind, fortunately for you, that encoding logic has been given to you. So objects in C++ and functions in C have actually been provided, where all you have to do is call the push bit function, and it just sends a bit to the bit stream. You don't have to worry about how it's being encoded at the end of it. That was sort of covered by the outcome of assignment 1. So the way it works is like this. If I have a bunch of bits and they form a bit stream, then I'm going to, so I'll have this sequence, 1 1 0 1 1 0 0 1 0 1 1 0 1. So I have this sequence of bits, and this was the first one. And this was, I guess, the last one. The way it works is this. When I push the very first bit, the question is, here's the first byte I have to produce. So obviously, as the bits come in, I'll group them into groups of 8 and then send them out as bytes. It's pretty simple the way this works, although it's a bit counterintuitive. It's actually the same as what compress does in its last stage. The first bit you give me becomes the least significant bit of the byte. The second bit you give me, and so I just do this. The second bit you give me becomes the next least, and then I just fill up the byte from least significant to most significant bit. Once I have a full byte, I output that complete byte. So this would be, 0x 4c, I guess. Wait a minute, no. It wouldn't be 4c, sorry, 0x4d, and then I output it, and then I start over again. And that's all there is to it. And I mean, I can just say that. I can wave my hands and say, well, you can't see it, but I'm waving my hands. I can wave my hands and I can say that's all there is to it, but obviously that's still a bit complicated. You've been provided, though, with data structures and things that do that. But we have to keep that in mind. That is consistent. We just push the bits in, starting at the least significant. Once we get all 8, we dump the byte out, we start over again. You also might notice that is actually pretty easy to implement. We can do that without any clever data structures. We can do it with an unsigned char and a counter and a bunch of functions that work with it. So don't worry about implementing that. Obviously, on assignment 3, this might come back because you will have to define your own bit stream. But for now, the bit stream is pretty consistent, and this part has been provided to you. But then there's this. I spent some time in February and March, I think, implementing this assignment from scratch, and that's without having all the tools and lectures and things that I'm providing. But I found the most frustrating thing to be not realizing what they meant by numbers. I know that sounds strange. The RFC contains a remark that says, whenever we put a number into the bit stream, whenever we do that, we push the least significant bit first. So if I say, if I have a 3-bit value, and let's say it's the number 5, I'm realizing that's a terrible example. So let's say I have a 3-bit value and it is the number, I won't edit that out, you can gloat about my mistake later. So we have the number 6 in 3 bits. That is from most significant to least significant this value. Maybe you can see why 5 was a bad idea. What this is saying is, anytime at all you have a value you are working with gzip or deflate that is actually a number, you don't always have one, but many values are supposed to be actual numbers. When you have that, here is how you put the number in the bit stream. You take the least significant bit, push that into the bit stream. So here's my bit stream. You put in the least significant, then the second least significant, and then the most significant. It doesn't matter if the number is 2 bits. It doesn't matter if the number is 32 bits. If it's a number, you always push it least significant bit first, always. That is rule number 1. And you will see in these slides, I keep referring to rule number 1. There is no rule number 2. Rule number 2 is make sure you follow rule number 1. When I was implementing this, I got that point. I figured, okay, right, when I'm pushing my 16-bit size value, I'll push it least significant bit first. Okay. And then I ended up pushing 3-bit values and not realizing, wait, those are numbers. Those go in least significant bit first. That is rule number 1. And if we follow that, what's interesting about it is absolutely consistent. I was grumpy about it when I wrote the code myself, but hey, it worked. If I follow the rule religiously, it does actually work. We just have to make sure that we understand that every number goes in least significant bit first. Now, why did I say every number? That's because there are things I push into the stream that are not numbers. They actually are just bit sequences. So for example, we'll eventually get to a point where we have these prefix codes. So there's A, there's B, I don't know, A's encoding is 1101, B's encoding is 001. So the encoding is a bunch of bits, but is that a number? Well, no, it is a sequence of bits. So if I push a sequence of bits, like the encoding I get from a prefix code, then I just push it from left to right. So I push this bit, then this bit, then this bit, then this bit. So rule number 1 only applies to numbers, not just to any sequence of bits you have. That'll be significant, and that's maybe a cause for some frustration, but there is only that distinction. Is it a number, or is it actually already a bit sequence of some kind? And we'll see that really it's either a number or it's a prefix code thing. There aren't really many other occasions to end up with bit sequences besides prefix codes. Okay, so the header itself is described in the RFC. I really encourage you to take a look at it, although you'll probably want to take more of a look at RFC 1951. I want to talk about, because the header is pretty much forced on you by the assignment, and you're actually provided code that generates the basic header anyway. I don't want to belabor the point. So first, we begin with a 2-byte magic number. 0x1f, 0x8b. And you might observe these are numbers, so you know how to handle them. Then we have 1 byte, which is supposedly the compression method. Now, the RFC says, sure, there's all sorts of compression methods. I tried playing with that, trying to reverse engineer what people would do to screw around on the assignment. For some reason, the gzip decompressor won't accept anything but deflate. It's not putting up with that attempt to find a loophole. So you're going to set this to 0x08. That's the punchline there. Then there's this thing called flags, and this is a bit field, so it's you set the various bits to 0 or 1 to indicate that certain extra things are present. We're just going to set this to all zeros. You can take a look at what it means to set it to ones. You can add things like if you use gzip to compress files, you could encode the original file name. You could add arbitrary text comments or things. That would set bits in the flags field to 1. If those bits are 1, then after the header, you'd have those fields later. We don't want that, so we're going to set flags to 0. Then there's this ModificationTime field, which is a 4-byte Unix timestamp. And so we treat that as a 32-bit unsigned integer, which is the number of seconds since January 1st, 1970. And we could also set it to 0, and we will do that. You're welcome to try and set it to something else. I don't know why you'd want to do that, but in the starter code, we set it to 0. It is a number, though, so if we want to push it in, we push it in least significant bit first. We see rule number 1 for that. This is another flag field. And this is supposed to be flags that are specific. So while this was flags specific to the container, this is apparently supposed to be flags relevant to the compression format. But those never materialize. There's no real flags that are worth setting here. I believe Deflate has a couple of flags you can set, but they're irrelevant to what we need, and so we'll set them to 0. And then there's this other field as well. So you might notice this is we shouldn't single out gzip here. You might notice a lot of these header fields seem to be completely useless. Why do we have them? Well, they defined a standard and now they're stuck with it. And we'll notice this isn't specific to gzip. A lot of standards have this problem where they define all sorts of strange features and nobody ends up using any of them. They end up using a very small percentage of them. Bzip doesn't have many of these things. Bzip, though, has a very bloated bitstream in some ways because it includes all sorts of settings that nobody ever seems to need, but that take up lots of space. They're not even optional. And even formats like JPEG and PNG have stuff in them that may have been easier to avoid in hindsight. So there's this other field at the very end called OS. And this is supposed to contain information on what operating system was used to originally encode the file. So why would you care about that? Well, maybe back and think about the way they might have considered this in 1988 or something. Maybe that was, nowadays we've got basically Unix-esque platforms, so Mac OS, Linux, and we've got Windows, and we know of a few differences between them, but they're relatively minor. They have directories and files, and they have multi-users. There's a funny line ending thing between Unix and Windows, but they have a lot of similarities. Think back to the ecosystem of different platforms in the late 80s, where you had all sorts of strange limits on length of file names, how many bytes could be in a file, ways files were stored, what a user was, if there are users, and so this flag was intended for you to indicate what operating system it was encoded on. So if you're decompressing, you could say, "Oh, I'm on Unix, and this was encoded on some DOS machine or something. I better make sure to account for potential line-ending problems." That I think is the most obvious one that carries to a modern setting. However, RFC 9052, in a typical sort of datedness of standards, the way that this works is, nowadays I would say if you're going to worry about line endings or what a file is or file name things, make up a flag byte and just set, bit 1 to be 1 if there's if the line endings have this format and 0 otherwise, or whatever. Just have it be use-based. Instead, the RFC says, we'll just assign a number to each OS, and you just choose which one is your OS. And the problem with that is, what if you invent new OSs? And also, what happens when OSs cease to exist? So I have RFC 9052 up on the other screen here. Here are your options. OS 0 is anything with a FAT file system. FAT being this, FAT, all caps, file allocation table. If you took 360 with a certain instructor, then you might have heard of something called FAT32, I think. Somebody, when they cover file systems, likes to talk about this specific one. The original FAT file system ceased to be used somewhere in the mid-90s. That's option 0. Option 1 is Amiga. Okay. Option 2 is VMS, and helpfully also OpenVMS, whatever those things are. Also dead. Option 3 is Unix. We're going to use option 3. Option 4 is Atari. Option 5 is the HPFS file system, which would be used by things like IBM's OS2, long gone, and Windows NT. NT, of course, stood for New Technology. I'm sure that's aged well. Option 7 is Macintosh, but not modern Macs, because modern Macs are actually Unix machines. This is the old Mac OS. Option 8 is Z system, okay. Option 9 is CP/M, also gone. Option 10 is something called TOPS 20, all caps. Option 11 is NTFS, also Windows NT. Option 12 is QDOS, and option 13 is something called Acorn RISC OS. Those are the only options. Hard to tell what to do with that. We're going to use option 3, which is Unix, and I will extend that to say Linux, but that's all that, and I think these days every compressor uses that. These other codes are completely useless these days. So we can't blame gzip for that. That's just a problem when you define a standard. There are certain things that don't age well. So we have the header defined, and of course the header could be bigger than 10 bytes. If we set these flags things to 0, though, the header is as small as it can get. Those 10 fields, or these fields, these 10 bytes must always be present. If we don't have anything else, then after the header comes a set of compressed blocks. There could be one of them, there could be 100 of them. And it turns out, because we're forced to use Deflate, all of these blocks are in Deflate format. So we'll talk about that later in this lecture, apparently. I'm looking forward to that. But the key thing there is that the compressed blocks could have any number of bits in them. So there could be a block of like 17 bits. The key is within each block. So this for example, could be 17 bits long, and this one could be 3 bits long, and that's fine. The beginning of block 1 ends 1 bit after the end of block 0. There's no need for padding between blocks. However, after the end of the last block, and each block contains a flag to indicate whether there's any more blocks after it. After the ending of the last block, the bit stream is padded out to 1 byte, which means that the footer bytes are aligned at a byte boundary. So that's a key thing. It's fine to have 2 blocks mashed together inside of a byte, but between the last block and the footer, we have to pad out with zeros until we hit a byte boundary. And so that's what this says. So we'll get to that in a minute. And then, after the block stream ends, we start at the first byte boundary there. We have these 2 4-byte values. And so they are numbers, and they get pushed according to rule number 1. So the first one is a CRC32 checksum. So CRC32 is a particular checksum algorithm. Because we don't want to argue too much about that, I've provided code from an open source project that computes that for you in the assignment. You can use it if you want. You don't have to. I don't see why you wouldn't want to use it. And the way it works is, as you compress the data, only the bytes you compress, so other bytes you add you don't do this with, but only the bytes, the raw input data, you compute a checksum as you go. And then when you're done, you store that checksum here as a 32-bit numerical value, which means rule number 1 applies. The reason that's significant is that way when the decompressor looks at it, the decompressor then computes the checksum as it decompresses and makes sure that it matches this value. Because if it does, that's a good sign that there wasn't a corruption in the bitstream or anything. You'll notice that we have to take this seriously because it's not optional. The decompressor creates an error condition if you do not have a matching CRC32 value. But you're provided with that, so I wouldn't worry too much about it. And then finally, this 4-byte value is the total number of bytes in the original uncompressed input. So again, not including any weird metabytes you add or whatever. It's only the actual size of the original uncompressed input. And because it's a number, rule number 1 applies. So I've provided some starter code. I'll have a separate video where I talk about the different starter code packages. The main starter code package compresses, it doesn't do any real compression. It generates a valid.gz file where it uses a specific deflate block mode that just stores data uncompressed. I've provided another starter package that shows off how to create blocks of type 2. So deflate has 3 block types, block 0, block 1, block 2. Block type 2 is going to take up a long time. And so I've provided a proof of concept example showing all the stages, although it's very sloppy. It doesn't do any of the stages well. It just puts them all together. And if you want to use it as the basis for your code, you can improve upon each part as you go. Because I know it's really frustrating to start from nothing and have to have a complete working example before you can test it. So the task then is to develop a program that encodes things into that format, probably based on the starter code I've provided. I don't care if it is or not, although I don't see why you wouldn't use it. And you can do whatever you want as long as this command decompresses it. That includes exploiting dirty tricks. As long as this command decompresses it, you actually, if you wanted to, could write a non-standard encoder that doesn't create a standardized file, as long as that decompressor decompresses it correctly. That one being the one on our common reference server. So if there are certain bugs in the gzip decompressor for Ubuntu 18.04, which is the environment we're using, you're welcome to exploit them. I don't know why you'd want to do that, but the sky's the limit as long as it decompresses entirely correctly. And some of the marks are given based on clever tricks you employ to achieve better compression. And so take a look at the specification. It provides a sort of menu of different things you can do to get the last few marks. So I've also created this program called gzstat. It's open source. If you have any pull requests, those would be welcome. You can look at the source code for it. It's in Python deliberately, not only because that's easy to write, but also so that you can't cannibalize too much of it directly. You'd have to try and read it if you want to steal code from it. But you're welcome to look at the code for it and modify it. There are ways in which it's not perfect. You can use this program to print a debugging summary of what's in a .gz file and maybe validate if it decompresses. But keep in mind, the only thing that I consider to be a validation mechanism is this command. So even if gzstat says the file looks good, unless it decompresses with gzip-d, I don't consider the compression to have been successful. But you'll notice that gzip-d basically tells you error if it doesn't like your file. It doesn't really give you any explanation as to why. And the way I debugged mine is I had to go into the source code for gzip and begin adding a bunch of instrumentation for it to tell me where it was complaining. Internally, it computes all sorts of error details, but never actually prints them out, which is pretty annoying. So here we are. It's been 30 minutes. We're 30 slides in. I can already feel the sore throat coming on, and we've got more than 100 slides to go. So we're inside of this middle bit, compressed blocks. And we'll see that for the most part, the number of blocks in your file is sort of your choice. Well, there are places where you will probably have to choose to make more than one block, but theoretically you could have the entire file dumped into one block unless you use a specific block type. There is exactly one block type called type 0 that does have a size limit, and it's the simplest block type. Block types 1 and 2 do not have a size limit. So which blocks to use and which types they have is a choice of the compressor. So from the previous lecture, the LZ lecture, I mentioned that we're getting into this place where the compressor can make a lot of decisions, and that makes it difficult to make the best decisions because there's so many of them. But it also means you can choose to follow a sort of compression workflow based on whatever you think is convenient or whatever you think is effective. So the deflate specification, so what deflate bit streams are supposed to look like, keeping in mind that deflate bit streams, these blocks, they could show up in other formats. So again, zip files, PNG files are examples of that. The format of that is given in RFC 1951. And I, as I said, was a bit grumpy about parts of it, but it is actually thorough, and it isn't, it contains very little unnecessary information. So it's actually a pretty concise read, I guess. And I would encourage you to look through it because it actually contains some details that I don't have time to talk about that are minor but might help you in achieving the ultimate goal of maximizing compression. So, yeah, just good. The slides agree with me on that. So all three of the deflate block types, and I don't know if it's explicit about this, but there are block type 0. Oh no, sorry, actually there is a slide coming up that talks about this. There are 3 different block types we can use, and all 3 of them start with this 3-bit header. And the first one is a single bit, 0 or 1, is this the last block? Because there's actually no real indicator for whether the block, when the block is over, whether it's got anything after it. And there's no way to detect that except if you've been told in advance. So you do have to keep track of when you write a block, will you be writing another one? Because it needs to know or else the decompression fails. And then block type is written in 2 bits. There are 3 block types, even though there's the potential for 4. Nobody ever designed a block type number 3. One thing that annoyed me was that the RFC 1951 talks about stuff like block type 10, which is meant to be, you know, block type 2. And I thought, okay, block type 10, so I'll write B type equals 10. No, rule number 1 applies, so I write 0, 1. And so that's one reason why we have to actually pay attention when we hear rule number 1. It is serious. Every number, even a 2-bit value, must be pushed least significant bit first. So this is the is last thing. I don't think this is too confusing for people. And then this points out that issue with rule number 1. And then after the block type is this bit stream, which could be just about anything. And we'll see each block type has a couple of other little details. So block type 0 has a brief header. Block type 1 is just a bunch of encoded data. Block type 2 is a pretty bulky header followed by a bunch of encoded data. So this can depend on the block type. So here's our list of block types. Formally, block type 0 is called store, so it's just a bunch of uncompressed data. That's it. There's no compression whatsoever attempted. There are cases, and you put a bookmark here for an exam question, there are cases where for some reason it is actually more efficient to store things uncompressed than with either of the other types that use compression. Because maybe we have an input that's just so hard to compress that it's better to just, call it and expand it a little bit by storing it uncompressed versus letting it expand more by storing it with one of the other types. There is no block type 3, and we won't want there to be one once we're done with block type 2. Trust me on that. Block type 1 is a combination of gzstat, which you should know about hopefully, and a fixed prefix code, so a hard code into the standard. Block type 2 is gzstat and a prefix code that you specify in the block header. And the prefix code, of course, prefix codes are pretty bulky. That has been compressed in some other way to make it easy to store in the block header. So we'll go through in order. And we'll need to because it's important to build up some resistance, I guess, for what's coming when we finally get to block type 2. So here's block type 0. Block type 0 is our is last flag, our block type flag, which of course for block type 0 is just 0, 0. And then we pad out to a byte. So you can see here this is 3 bits, and so block type 0 likes to be byte oriented, so we just pad out to the byte boundary, so it's 5 0 bits. And then we write the length of the uncompressed data, and then for some reason it's complement, and then a bunch of uncompressed bytes. And so I think the reason that they do this, you'll see in my other video that I post after this one about how gzstat and the starter code packages work. I think the reason they pad to a byte here is because then your actual, the uncompressed bytes of data you write will also be byte aligned. So you'll just be able to see them in the bitstream as bytes. They won't be on a funny boundary. I think that's why they did this. Otherwise you don't expect compression people to waste 5 bits. So I think it's for the convenience of, hey, if you're doing things uncompressed anyway, what's 5 more bits for the sake of seeing your data? After your padding, you write a 16-bit unsigned value, which is the number of bytes of data in the block. Because keep in mind, there's no other way of identifying the end of the block from this, stream of bytes. So you can't use a null terminator or something. So we write the 16-bit block size, which of course implies a limit on the size of a block into whatever you can describe in 16 bits. Then, for some reason, and so just to be clear, sorry, rule number 1 applies. It's a number. For some reason, we then store the bitwise complement. And just to remind ourselves what the bitwise complement is, here is the number, I'm not going to use number 5 again. Here is the number 7 in 4 bits. The complement is just flipping every bit. And to be clear, if I say I'm going to write, I would rather use an unsigned value here. So unsigned char x equals this. If I want to define what, well, okay, I should write 0b to make sure it's a binary value. I could also write y equals this symbol x. The operator, this operator is the bitwise not operator in C and C++. So I could also write this. It's going to point that out. So it's weird to think about that. This doesn't give me any extra information. I mean, this is the same value, but with all the bits flipped. Why am I storing it twice? Well, we've already wasted some space. Why not keep going, right? I think this was some sort of an error checking thing. They figured that if they saw a bunch of zeros here, how do they know that this is actually a block of type 0 and not something else? And so I think maybe somebody thought, well, what they'll do is have you write the length twice, and then the decompressor can check that the links match up in the way they expect them to. It otherwise doesn't make much sense to me why they would deliberately waste 16 bits like that. But in any case, that's lost to history now. Once we do that, we then write all of the uncompressed bytes. It'll be this number of uncompressed bytes. We just write them out. And then we follow that with the next block or with the footer or whatever. So that's block type 0. That's not so bad. That only took 6 slides. And oh yeah, this is pointing out, so you do get that implied limit on the size of a block because you can only give a length of a certain magnitude. So I provide a starter code that takes data and just encodes everything into blocks of type 0, which means it does have to encode multiple blocks because your data could be too long to fit in one block. And so that should give you some idea of how a header works, because it does generate a fully compliant gzip file, and it should show you how to write the individual bit fields here with the automation I've already provided. But of course, block type 0, there's a long way to go from there. We want compression. This does not provide it. So we can talk about blocks 1 and 2. So first, these two block types use a combination of what is we know this now to be LZSS encoding. The RFC annoyingly calls this LZ77, which it is not, and a prefix code, which the RFC annoyingly calls Huffman coding. Now, if we know what's good for us, we'll probably use something like Huffman coding to compute the prefix code, but actually it'll tolerate any prefix code that satisfies the Kraft-Macmillan inequality at exactly 1, and a couple that don't in some cases, but there's the way it checks is a bit peculiar. You'll notice I've provided a basic example of block type 2 that doesn't even attempt to build a Huffman code. It just builds a sort of bogus prefix code that the decompressor will work with. So we'll notice the RFC, and this is what I mentioned when we talked about Huffman coding. There's this annoying metonymy thing where it's like prefix codes for some reason are just called Huffman codes, even though Huffman codes are a subset of them. So the way that this works is we transform this stream of symbols, which in this case is a bunch of 8-bit values, into a stream that combines literals, so 8-bit values, and length distance pairs. And then we take, so this is actually going to use a larger symbol alphabet. We actually define special symbols for these length and distance things. We then take the result and we encode that with a prefix code. So what's interesting is what we're encoding, the symbols in our prefix code are not just 8 bits. They're actually a strange odd number. There's 285 symbols that we end up needing to encode. And you might think that's sort of wasteful. Why not use 512? But keep in mind, the idea of using powers of 2 only makes sense if you're storing in fixed width. You can use an arbitrary number of symbols if you're using a prefix code because there's no real correspondence between the number of symbols and the number of bits you get because they can have variable lengths. So we should talk about exactly how the LZSS encoding works. You've already seen how does LZSS work in a vacuum. So I mean, like, what is this all about? But I mean, you should appreciate we can't encode 5:9 into binary format without thinking about it a bit more. And we mentioned in the Limpel-Ziv lecture that okay, we could try encoding them with fixed width things. We could say our back references have a length field which is 5 bits or something. It's not as easy, it's not as simple in Deflate. And I foreshadowed that by pointing out that there is a manner in which it tries to encode shorter back references, so things that are from more recently are encoded in hopefully fewer bits. But the window size is 32,768, and that includes, just to be clear, if I have 3 blocks here, so there's block 0. Actually, sorry, I'm going to call this block 10. I don't want you to confuse this with block type 0. There's block 11, and there's block 12. If I am encoding block 13, and I am looking at this character here, I am allowed to make back references into the last 32,768 characters, even if those characters bridge over into previous blocks. I'm literally looking at the last 32,768 decompressed symbols, and I'm allowed to use any of those for my back reference. There's no requirement they be in the same block. There's also no requirement that these blocks have been encoded with LZSS. They could have been encoded with type 0. It makes no difference. Just any of the previous 32,768 characters. The look-ahead distance is 258, strangely. I know, again, that's an arbitrary number. So it uses a sliding window of this number of history characters and this number of future characters to construct this LZSS stream full of literals and back references. I mentioned this in the previous lecture because I think that distance length pairs are easier to describe, but for a bunch of strange reasons, back references are always encoded with length first. That's going to be significant because the way we encode length symbols versus literal symbols is going to become a bit of a thing in a minute. So just to be clear, this is a back reference of length 5, 9 characters before the current position. It's worth considering. You won't get full marks for this, but it's worth considering, as we saw, participation in an LZSS scheme is sort of optional. You can choose how many back references, if any, end up in your stream. It's not like LZW where you have to do things a certain way. And some of the optimization you have to do is it worth emitting or looking for a back reference here or not? If you completely omit the LZSS logic, you won't get full marks, but it's perfectly permissible, and you might get more marks if you selectively omit certain back references. So here's the problem. Ultimately, it's this. I have this weird stream of now apparently 8-bit character values and whatever this is. And I think, okay, so I could define an alphabet where I have all the 8-bit character values, and I define a new symbol for every possible back reference. And then I have this massive alphabet, and I make a prefix code for it. So the problem with that, there's a lot of problems with that, but the big one is that defeats the purpose of a prefix code, which is that obviously I want there to be some way for back references to have frequency greater than 1. And if I have a different symbol for each back reference, how likely is it I'm going to see too many 5:9s, right? Or, you know, more concisely, things like 10,000:15 or something like that. That's a hard one, and so there's a need for some nuance there. There is, of course, also the other thing of I don't want to have to make up a symbol for every possible, let's see, so I would have, if I have a symbol for each possible length distance pair, the number of possible lengths is 258, because that's how big I can have up to that number of things in my future, times this number. I do not want to have to make a prefix code with that number of symbols for a lot of other reasons that are very practical in nature. So that won't work. On the other hand, I do want to allow my back references to participate in prefix coding somehow, because I sort of have no choice. Otherwise, how do I integrate them in the same stream as other things that I'm encoding? I need some way of saying, after I've encoded up to here, hey, the next thing is a back reference. So I need to think about how to do that. We'll see in future schemes that there are plenty of schemes that don't even bother including weird meta things like this into the prefix code. They just add a special symbol to the prefix code that says, hey, the next thing up isn't actually in the prefix code. That's fine, but Deflate doesn't do that. And we'll wish it did soon, but unfortunately it doesn't. Instead, what it does is it takes each back reference and encodes it it breaks it up into pieces, and then encodes some of those pieces with a prefix code, and some of them it encodes as binary numbers. And basically it comes down to, the only thing I need to really do is be able to, when I've done decoding the space, I look at whatever comes next and say, oh, that's a length or something. And then I can behave differently, thinking I just read a length, I guess I have to read a distance or something like that. And so Deflate does this. It uses two different prefix codes. So two different alphabets with completely separate encoding tables. One of them encodes all of the possible literal characters, so all 256 1-byte characters, and also values for lengths. So all lengths and literals go into one alphabet. A separate coding table is used to encode distance values. The logic there is basically, okay, I'm decoding, I assume I'm always decoding a literal or a length, so I decode this, and I keep going. Eventually I get here and I decode the length 5. And I think, okay, that's a length, so now I will go and decode a distance with the distance encoding. And I'll use the distance coding table and I'll decode a 9. And so there's no need necessarily to use the same set of symbols and have it contain both lengths and distances. I just need some way of differentiating lengths from distances and lengths from literals. So here's what we do. We define the symbol set to be symbols 0 through 255 are our usual 8-bit sequences. They are the literal values. We'll see this in a minute, but symbol 256 has a special meaning. It is the symbol to indicate the end of a block. Symbols between 257 and 285 are a way of encoding a length, and they encode it in a sort of telescoping representation. So if you see the symbol 258, I am referring to length 4. But on the other hand, lengths can be up to 258, so I want to use a small set of symbols here. If you see the symbol 260, I mean length 6. If you see the symbol 264, I mean length 10. Great. If you see the symbol 265, though, I mean length 11 or length 12. So some of these length symbols correspond to multiple different lengths. So for example, 274 corresponds to lengths 43 through 50. And the way this works is, after some length symbols, so not all of them, but after some of them, there will be extra bits present, what I'm going to call an offset, that describes which of the lengths in that group am I using? And it's just a number. So here, 43 and then 8 and then 3 bits means that there are 8 possible lengths that correspond to symbol 274. And they are 43, 44, 45, 46, 47, 48, 49, 50. So all I do is I take the offset, I look at the next 3 bits, I take that as a number, and I add that to my base length. And that's what length I'm actually encoding once I've seen symbol 274. And you'll notice what's convenient about this, maybe I'll show on the next slides some concrete examples of this. What's convenient about this is if you see symbol 257, you're looking at length 3. No extra bits needed. And that's maybe because you're more likely to see back references of short lengths. You want to have back references of long lengths. So for example, lengths 163 to 194, but you'd rather not, waste short bit sequences on those. So instead, we use symbol 282 and then a 5-bit offset, which does take up more space than just using a symbol by itself. But it's a good balance of the less likely long back references get longer encodings than the more likely short back references. And so that the slides agree with me. And so this is giving some concrete examples. Just to be clear, the way this works is if you want to encode a specific length, you find the symbol, the largest symbol value whose base length is below the length you want, and then you subtract that off. So let's say you want to encode, this is using the example 21. So I find the smallest symbol whose base length is less than 21, it's this one, and then I subtract 19 from 21 to get my offset of 2. And then I encode that in 2 bits. If I want to represent the length 202, I would find this symbol, which is 195. I would subtract 195 from 202, and I'd get the number 7, and then I would encode the number 7 in 5 bits. So you can encode any length between 3 and 258 by using this mechanism. It's interesting to note that for some reason, the last length, 258, has 0 offset bits. That's a good thought question. There's actually a very practical reason for that. And it's significant that it's because it's the last length available. If you don't, for these symbols that only have one length, so base length is 6 and offset bits is 0, you don't need any extra bits. You just encode the length symbol and that's it. So this is belaboring the point a bit more than I would have. And then once I've seen a length and its offset, I encode the distance using a different symbol table. And because we know once we see a length that a distance is following, I don't need to use the same large alphabet. I can just use a separate alphabet that starts at 0. So there are 29 distance symbols, and they're encoded the same way. You'll notice that because distances can be much larger than lengths, we get up to some pretty large numbers and some pretty large offsets. And again, the offsets get bigger and the ranges get bigger as we go further back in our history, which makes some sense because you can imagine generally we might see back references going back thousands of characters, but odds are a pattern in our text is more likely to be a little bit local. And so we want distances that are short, so 10 characters ago or 20 characters ago, to be encoded in a small number of bits. Whereas long distances, if we have to go this far back and use 12 extra bits, maybe there's something useful back there that's worth it. But this is a place, and I mentioned this in the gzstat discussion, that because of this, because encoding a distance this large takes so many bits, it might be that a back reference of a certain size this far back isn't worth encoding, where it might be worth encoding if it were closer because of all the extra overhead needed. But that's the trade-off. We need to have, we still need the benefit of having back references that are not very far back encoded in as few bits as possible. So the maximum representable distance is 32,768. So whether you want to keep a larger window or not, it makes no difference because you can't store distances that are that large. So the largest distance you can store is the size of the history window that we already defined. I want to sort of talk about, now that we've seen the encoding a little bit, I want to go through this from scratch. So first, I take my sequence of bytes. Then I stick an end of block marker at the end. So just like in previous lectures, when I'm working with 8-bit values, anytime the value can be written as a character code, I'll just write it that way. But of course, this is the number 65. So I take my original data, I then stick an end of block marker. So I've decided this is going to be my block. Maybe it's my entire input. Maybe I cut my input off and decided to split it. Who knows? But when I have a block, I add my end of block marker to the end. So it's going to be symbol 256. In my literal and length alphabet, it's a special symbol that always appears exactly once at the end of each block and nowhere else inside the block. And then I take the result, I apply LZSS to that, and it's significant, I think, that we put the end of block marker before we use LZSS. Although to be clear, any back reference that goes across a block boundary only considers the real uncompressed data. So if I'm sitting in a character far along the line after this block is ended and I'm looking for back references, this is invisible. This is just a sentinel to indicate that a block ended. It's not considered to be part of the data for the purposes of a back reference. And so just like before, I'm going to point out that which back references you add is your compressor's decision. You can choose to ignore certain ones. You can choose to stop looking after a while. You could decide only to look a certain distance back or only for ones of a certain length. You have to make sure you write code that is generating some back references because that's a learning outcome. But you are free to ignore certain ones or to use special optimization logic that avoids using generating back references that are not practical for some reason. It is worth considering, and this we can see this, it's dictated. We can't encode back references of length less than 3 because there's no length symbol for it. So that's one choice we don't get. And we saw LZSS doesn't like back references of short lengths anyway. This is one reason. Basically, it's easier to encode 2 literals than it is to encode a back reference of length 2. And so maybe I'll fix this slide before I post it. What's getting cut off there isn't really that important, but for the sake of the next example making sense, we maintain two different prefix codes, one for each alphabet. I have completely made these numbers up. And we'll see in block type 2 we can do that as well. But the reason these numbers are here is only to give some context for the slides that are about to come. I guess I mentioned at the beginning, there are some slides in here that I haven't seen in weeks because of how long this lecture has taken to put together. So suppose we have these two coding tables. And we're just using arbitrary values for the codes. And the key idea, though, is just to give you some perspective for these numbers we're about to see. We'll notice in block type 1, you have to use a specific code. And in block type 2, you can make whatever code you want. So there's nothing significant about these tables. It's also worth considering that there might be some codes that never appear. There are cases where you will have a code table where certain values do not get an encoding at all, because you never use them in your block. You might use them in a different block, but if you don't use them in the current block, they don't need to participate in the code for the current block. So for the rest of the lecture, I am going to call this the LL code, because it's the literal length alphabet. They share one big code table. I will call this one, of course, the distance code. That's the logical term for it. So how does this work? I start by taking my input sequence after applying LZSS, with my end of block marker there as I expect it to. And the first step is I take each symbol and I either represent it as a literal. So here, there's no back references. These are just literals. Or I represent a back reference as this sequence of four things. My length symbol, whatever offset goes with it, my distance symbol, and whatever offset goes with that. And then I figure out how to encode each thing. So of course, all the literals get encoded by the LL code. There's no other choice. The length symbol gets encoded by the LL code. The distance symbol gets encoded by the distance code. The offsets get encoded with some number of bits depending on the length symbol. In this case, this offset is 0. The length symbol 257 is the length 3. It turns out that if you go back to the table here, length 0 has 0 offset bits. So I don't even store the offset at all. I just leave it in, I store it in 0 bits, so it doesn't end up contributing at all. Distance symbol 4 is the one I use for the distance 6, and the distance offset is 1, and I store it in 1 bit. And we'll notice these are numbers. Offsets are numbers, and so rule number 1 applies. We must output the least significant bit first. And then these three things are literals. So we get this. And this is why I gave those bogus codes. So just in case you're wondering where these bit sequences come from, these are just taken out of this arbitrary code I provided for perspective. We'll see examples of actual codes later. So here is the encoding, the bit stream I would come up with for my literal values here. Here is my length symbol encoded. I don't have any bits here. That's just a blank space. And then I encode my distance symbol, and then my distance offset, and then the rest of the literals. And then the complete deflate bit stream for the block, after the block header or whatever else, is just this. And of course, I push the bits starting here. Now it's a bit stream, so I just push the bits in order. And just the slides reminding, these are just arbitrary for the sake of having something for this example. Now, as we can see, if I have these big back references to encode, so this is a length distance, so a length of 187 going 578 characters into the past, then I end up with these offsets being pretty big. Even if, so we'll notice later, there's no reason why symbol 282 has to have a long encoding. If I see lots of back references going with length 187, maybe length symbol 282 has a 1-bit encoding. Who knows? But I do know that definitely when I'm working with length symbol 182, I have to encode my offset in 5 bits. And that goes least significant bit first. So I do have this bulky offset, and it gets bigger and bigger as the distance or length goes up. This is a sort of a fundamental assumption of the deflate specification, which is that back references that are further in the past and back references that are longer are less likely to occur. Certainly, if you're lucky, you'll get back references of length 258, but it's not as likely to see those as it is in average data as a back reference of length 3. So now we have to talk about prefix codes. So just to be clear where we are in the lecture, we are not yet at block type 1 yet. We're hopefully going to get there sometime, but not just yet. We have one more thing to define, which is we're going to talk about prefix coding. Now again, the RFC keeps calling these things Huffman codes, and fair enough, I guess. The way that it stores a code in the file, if it needs to store it, is with a table of its code lengths. That's it. Now you've seen before that we have this standard algorithm that we take our table of code lengths, we sort it by length, and then we generate our code based on a standard algorithm, this canonical thing. Gzip and Deflate use the same basic algorithm. They provide pseudocode for it. It looks a bit different than the one we've seen, but it does pretty much the same thing. I have actually provided an implementation of it in one of the starter code packages, so there's no need to copy it from the RFC yourself. I've already provided it. And it's important, of course, that we use code lengths to define the code, but we have to all use that algorithm to compute the actual code values, because if we don't, we're not going to get the same code the decompressor thinks we're going to have, because we never actually put these encoded sequences in the definitions we give. We use them, but we don't actually put them in and define them, because we assume that if we give the decompressor this table, that's all that it needs. So it's very important that we do use that canonical algorithm. The source code of gzstat contains it, and actually it turns out that one of the C and C++ starter packages, the one about block 2, also contains it. What I recommend doing, so we talked about this a bit before, you can generate Huffman codes, if you're clever, in a way that gives you this ordering so that you have this code to begin with. If you want to avoid the headache, you could always just do arbitrary, like basic Huffman coding, and then take the code links out of the Huffman tree and then regenerate the code by feeding it into this algorithm. That way you're guaranteed there's not going to be some discrepancy between your code lengths and the ones actually used. I know it's an extra step, but it's a linear time extra step, linear in the code, in the number of symbols, so it doesn't cost that much to do it. And it's probably, the amount of computer time it uses up is negligible compared to the amount of brain energy it would use up to make sure your Huffman coding algorithm will always produce the code you expect it to. So it's better to use Huffman coding to produce anything and then take the code and sort of wrangle it into shape by running it back through the canonical code algorithm, which of course is very fast, so it's not that big of a deal to do that. Okay, so I'll have some of my beverage. Hopefully you've all gotten beverages out there. This must have been a rough couple of hours. We're finally ready to talk about block type 1. We've done it. We've gotten to 2/3 of the way, 2/3 the number of block types. So block type 1 starts with our isLast flag, and then of course the B type flag is set to be 1, which, just to be clear, that would be the binary value 0, 1, which is pushed least significant bit first because it's a number, so rule number 1 applies. And the bit stream is computed, as we just described earlier. We first compute our symbol stream with LZSS, and then we can convert that to this stream of LL symbols, so literals and lengths, as well as offsets and distance symbols. We then take it and we use a fixed LL code. So it is encoded, it is hard coded into the standard. It is the code that you would produce with a standard algorithm with these code links. That is it. It is always that code. So there's no variability allowed. You must use this code in block type 1. The distance code is even simpler. It is the one you compute with a standard algorithm where every length is 5. That's it. So there's no more magic to it. If you want to encode in block type 1, you get up to about this point here, and then you use that LL code with those links I defined and the distance code with length 5 after running through the standard algorithm. So in block type 1, you can use LZSS. You can get legitimate compression out of LZSS and back references. You might get some compression out of this. You might notice that the way this is defined gives on characters that are the usual printable characters, so 0 through 127, you get code length 8, which means you break even. They're in 8 bits. For these ones, which maybe are a little bit less common in some data, it's 9 bits. But on the other hand, these symbols, most of which are, all of which are length symbols and the end of block marker, it's 7 bits. So you save a bit on that, and then these are 9 again. The reason it has to alternate is because you can't have everything in 7 bits or everything in 8 bits. You have more than 256 possible symbols, so you have to sort of trade off. So, if you want to generate block type 1, here is what I recommend doing. And it's worth doing this because even if you want to go for block type 2, you can more easily test your LZSS logic on a simpler block type. First, build up a block of input data. Who cares how big it is? I don't know, 100K? I mean, whatever is a convenient size for an array. It's your choice how many blocks you have and how big they are. Take the data, add your end of block marker. Then apply LZSS and break the stream up into those LL code symbols, those distance symbols, and those offset values. Then apply the codes we just described to produce the actual bit stream. Now, the great thing about doing it this way, starting with block type 1, if you wanted to do it, you could jump right into block type 2, but the great reason I think that this is a good idea, that you should do this, is that this way you can spend some time figuring out how to get away with this. The codes and how to and how they're stored isn't a big deal because obviously you have this fixed code table and it doesn't need to be stuck in the bit stream because the decompressor knows that in block type 1 it's always this code. Block type 2, oh, here we are. So block type 2 is, we're ready for our final ascent. So we know that we can use LZSS. We know about the logic behind prefix codes. We know about this weird 2-alphabet model, the LL code and the distance code. We're finally ready to leverage all of the features. And there's no middle ground. You either use block type 1 and you get the fixed code, or you get to define everything yourself. So we use LZSS. Okay, we know about that. We can define our own prefix codes. We probably use Huffman coding or a variant of it to actually compute them. And we can use each block as independent. So of course I could define a prefix code for block number 5 and a different prefix code for block 6. I have to put the prefix code into every block with type 2. That's one reason why blocks of type 2, we shouldn't let them be too small because there's a lot of overhead that goes into that block header, which defines the prefix code. Okay, but how do we define the prefix code again? Well, I guess we saw from here we have to give the table of code lengths. So for each symbol, I give the length of its code. And the convention is if the symbol never appears, you're allowed to give it a code length of 0 to indicate that it's not even part, it doesn't get a code at all. Okay, but that's a problem because my LL code alphabet has 285 symbols. So I'm going to store a table of 285 things in the beginning of every one of my block? No, of course I'm not going to do that. I've got to find a way of compressing it. That's the whole point of compression. So here's where things get a little bit non-linear. So it's one thing to use Huffman coding or to run LZSS and then run things through a prefix code. The reason block type 2 is a bit of a nightmare, the reason that the complexity is ramps up significantly, is that we have to store these code tables, and the code tables are big, and we don't want to store them uncompressed. So we have to find a scheme for compressing them. Okay, so what do we know about? Well, we know LZSS, but how is the code table going to benefit from that? I guess we could define a prefix code. We've used those before. We could encode our LL and distance code length tables using a prefix code, a different prefix code. We will call this the code length code. Now you can appreciate that because calling things code length codes is going to be a nightmare, I will just say CL, and we'll just agree with each other that it's better to use the abbreviation there, the CL code. The reason why that's especially tough is that we eventually have to talk about the length table for the CL code. So to clarify, the CL code is the code length code, so we're talking about the code length table. We do not want to do that. So the CL code is a specialized code with a very small number of symbols that's used exclusively to compress the code length tables for the LL code and the distance code. But if I want to define the CL code, I generate a prefix code. So how is the decompressor going to know what that is? Okay, so what I do is I take the length table for that code and I encode that into the header using, well, the slides are being melodramatic, yet another code. It's fortunately not as bad as it sounds. We use a pretty basic code to encode the code length table. But maybe you can see here, it's our last ascent, right? We're almost there, but on the other hand, it's a bit of a steep ascent. It's been a brisk hike up to this part of the mountain. It's pretty much going to be scaling vertical rock from here on up. We've got quite a bit to do. Okay, so here's my recommendation. First, grab our block of data like before, add the end of block marker, apply LZSS. Okay, so we apply LZSS. We now have our set of length symbols, literal symbols, distance symbols, offsets. I am allowed to generate my own code for the LL alphabet and for the distance alphabet, which means if I'm going to do it properly, I should generate it using Huffman coding based on the frequencies of actual values, literals and lengths. So I should apply LZSS before I create the code so I can see which symbols, including length symbols and distance symbols, appear most often. So I get to this point like I was in block type 1 and I pause. I now go and generate prefix codes, probably Huffman codes, and then I find a way of encoding them. So that's going to take a while. We'll talk about it. And then once I've encoded them into the block header, then finally I go back to my LZSS stream and I just apply the codes to generate my final bit stream. Okay, so sorry about that. We'll fix that one. I'll make a note over here to fix slide 89. We're more than halfway there. So how do I compute prefix codes? Well, use Huffman coding. That's my informal recommendation. We don't actually have to do that, despite RFC 9051 saying Huffman coding. We could use anything we want. The decompressor strangely doesn't like it if you don't have this. It doesn't like an inefficient code for some reason. It doesn't care if it's a Huffman code. It requires that the formula evaluates to 1. We've seen, and you maybe saw this on the midterm, that certainly if it evaluates to less than 1, we could have done something easy to make the code more efficient. And I think that's what the decompressor is getting to. It's weird that it throws an error like that. That's sort of contrary to the usual design philosophy. The way that we should do this, no matter how you get the prefix code, that's what this cutoff paragraph is saying. No matter how you get the prefix code, you should, for safety, once you get your code lengths, recompute the actual code values using the algorithm, just in case, to make sure you definitely are working with the same code values. In my own debugging, I kept running into that. I thought, I'm sure my Huffman coding algorithm is generating a canonical code, and it almost was, and there was a bug, and I'd spent like a day on that. If you just run it through the algorithm, then the problem just disappears, and it doesn't take that long. The algorithm's pretty fast. So there's also this thing, though, which is that you can use Huffman coding, but there's one issue you have, which is that we'll see why in a minute, but you're not allowed to use code lengths of more than 15 in the LL and distance codes. And that means it's very easy. In fact, it's really easy for Huffman coding to give you really long code lengths. If you have an alphabet of 285 symbols, it would be really easy for it to give you potentially 285 or 284 as a code length. And so because of that, you have to have some arrangement for what happens if you do Huffman coding and then end up with a tree that's too deep with lengths of greater than 15. So you have a few options. We'll talk about this later. We'll spend some time in a sort of tutorial setting thinking about things like this. But one option would be to just do Huffman coding anyway. Go look at the tree, and then hopefully you're good. Hopefully the tree is of depth less than 15. If not, go find some leaves that are too low, and then find somewhere else to move them. So pull some stuff from a that's higher in the tree down, push the stuff that's too low up a bit, balance the tree a little bit. Now, of course, that can affect the optimality. Maybe you don't end up with the best way of doing that, but it is a way of doing it, and actually the real gzip encoder basically does that. There is this algorithm. It came up in the last week of May in the lecture. There is this algorithm called the package merge algorithm that is a generalization of Huffman coding that generates an optimal code but respecting the length constraints. You could also do that. And that's one thing where you also get some extra marks for actually doing that on the assignment. So but make sure it works. That's the important thing. So keep that in mind. We'll see that something similar happens with a CL code later, where its lengths are limited to 7, which is also going to be a thing. But first, the reason block type 2 is a nightmare, the reason we are ascending a vertical face of rock here with our bare hands and no chalk is that the way we have to encode our prefix codes into the header is it just twists your brain into a pretzel. There's so many weird variables and so many strange arbitrary obstacles that the format places. I was thinking about this in writing up the assignment specification. I was thinking, wow, is this scheme too punishingly arbitrary? Like, should I have given people, I don't know, bzip or something? And I implemented bzip as well, and so I went back and looked at my bzip implementation, and nope, pretty much the same problem. Not the same exact issue, not the weird code length codes or whatever, but also very strange arbitrary features, because it's true that it's complicated, but it saves bits. The reason that they've done this is because it saves bits, and ultimately, we're still using this program 30 years later for that reason. And that's why this extra complexity, although mind-bending, does have, there was a good reason why it was added. Suppose we have this. So I've computed, I've already gotten past my computation of my codes and code lengths, and I've decided that my 285 symbol, or 286 symbol, sorry, LL code table looks like this. So some things have length 0, and that's a way of signaling to the decompressor that they are not there at all. So there is no encoding for symbol 285. It will not appear in this block ever. I can't encode it. It has no encoding. And so I give it length 0 so that we don't include it in the code by accident. It's important because the fewer things are in my code, the more likely it is the things that are there get short encodings. And then here's an easy distance code. Everything has length 3. And there are some things that have length 0, but everything present has length 3. And so one of the reasons why we have such complexity here is that we need to be able to store small blocks. Small amounts of uncompressed data. I want the block to be small in any case, but I need to be able to have a format that still works if the amount of data I'm encoding isn't very big. So it's true that a 285 or 286 entry table isn't that big if I'm storing 10 terabytes of data, but it's a bit of a problem if I'm storing less than that, and especially if I have to keep changing blocks because I want to change codes or something. Because if I'm going to, if I have a file that's 100 megabytes in size, maybe it's more efficient if I can change Huffman codes every megabyte, because maybe the patterns change. So I need to have an efficient way of representing these code tables. And maybe that means that the block is small, and I need to be able to encode efficiently code tables for small blocks, where lots of symbols never appear at all. And that's one reason for this upcoming complexity. So here's what we do. We have our LL code table, and ultimately, these are just indices. We don't care about these. I don't need to encode these into my bitstream. So what I want to encode is this vector of lengths. And I look at it and I notice there are a few avenues there for some techniques we already know. And of course, all those techniques we learned in May were leading up to things like this. We notice stuff like, hey, there's a whole ton of zeros in a row. And hey, there's a whole ton of 5s in a row. Maybe we should use a scheme that allows us to efficiently collapse runs of the same length into smaller representations, and we have that. We have this special set of symbols called, I'm going to just keep saying CL, the CL symbol alphabet. And the symbols represent lengths, and the first 16 of them are lengths 0 through 15. And that's why our limit is 15 bits in an encoding, because the CL symbols don't exist beyond that. So if I want to encode a length table, I could encode it entirely with numbers between 0 and 15. So I could, 3, 3, 0, 0, 0, 0. But I also have these 3 extra symbols that I'm allowed to use for run length encoding. So if you see the symbol 16, that means I'll give you a 2-bit value, we'll call it x, and you take the previous thing you saw, and you repeat that x plus 3 times. That's sort of, we'll see in a minute why it's x plus 3 and not something else. So a 2-bit value here could be 0, 1, 2, or 3. So I could repeat it up to 6 times. And if you notice, that allows me to encode this long sequence of 5s. I encode a 5, and then I say, okay, here's symbol 16, x equals, let's see, x equals, sorry, it doesn't equal 3, x equals 1, because I want to encode 4 occurrences of the previous symbol. So I encoded x plus 3 times, x equals 1, that's 4. So that's one way of encoding the previous symbol. And then there's these 2 special symbols just for zeros to predict the fact that, yeah, we're probably going to have cases where our code tables have lots of long, large runs of zeros in them because we never see large numbers of different symbols. So this has nothing to do with the previous length. Code 17 in any context means repeat a 0 x plus 3 times. And I give you a 3-bit value, which means you could repeat it anywhere between 3 and 11 times with code 17. With code 18, I give you a 7-bit value, and you repeat the length x plus 11 times. So I can encode even longer runs of zeros with code 18. So remember, this is actually the code length code, because it's being used to encode a length table. I'm going to keep calling it the CL code because we have to do anything we can to keep this together. So I then take these length tables, the LL length table and the distance length table, and I encode them using this scheme into a sequence of these CL symbols, and occasionally little, sorry, this should just say X, these offsets, these 2-bit, 3-bit, and 7-bit values. So I end up with something like this. So this is the first bit of that LL code table from earlier. I encode 3 directly as a CL symbol, just as the length 3. I encode this run of 63 consecutive zeros as symbol 18, followed by this value x, 52, which is the length of the run minus 11. Notice that that's what this says here. So it should say x. But if I want to encode something of length 63, I encode x to be equal to 52. And then I encode my length 6, then my length 5, and then I see 4 more 5s. And I actually have the choice to just encode those literally, just like anything else, but I could also use symbol 16, and then the run has length 4, so I take length minus 3, and I store that as my offset. You might observe that depending on the way my length table looks, I might see certain symbols more or less often. If I have lots of runs of consecutive things, 5s or anything else, I might see symbol 16 a lot. And if I see symbol 16 a lot in one encoding and not very much in another, why should I use the same number of bits every time I encode symbol 16? Well, I shouldn't. Usually when we have this sequence of symbols, we try and adapt how we store them to the frequencies that occur in their representation, and so we use a prefix code. And so what we do when we want to actually store this sequence I'm generating here is we encode the CL symbols using a special prefix code. Of course, that means we now have to go define a prefix code and put that into the bitstream somehow. So we're just going up one more layer here of prefix codes that we have to store. Okay, so suppose I'm working with this sequence of things and I encode it all the way through and I generate an encoding of these two tables, so all of them together, so this entire vector and this entire vector as that sequence of CL symbols. I then look at the frequency of each symbol and I get this. So suppose I end up with this. This is, this is my code links. I compute the frequency of each symbol, and then I compute a prefix code based on those frequencies using Huffman coding or whatever. And I end up with, we noticed that we saw a lot of 3s. You can see a lot of 3s there. So maybe it turns out 3 gets a short length, and I don't know, 16 only appeared once. It gets a longer length. So now I have a way of defining a prefix code for the CL code. Okay, but how do I store that into my block 2 header? We're still talking about the block 2 header. So just to be clear here, I obviously don't know what the prefix code is until I have actually computed the stream of CL symbols for my length, my LL and my distance code table. So here is the sequence for the first half of the LL table. Here's the remainder of it, the sequence of CL values, and then here's the distance code table. But once I've done that, I can then use the resulting code, so what I computed here, I can use that to actually begin encoding. So I'd say here, I take the CL symbol, run it through the code. It turns out it just gets the single bit 0. Code symbol 18 becomes 110. This gets encoded just like the offsets before. It's a 7-bit value, and rule number 1 applies, so I have to encode at least significant bit first. It turns out the specification, I'm just pointing this out so that people don't accuse me of leaving it out somehow. You don't have to do this. You are allowed to encode the LL and distance tables as one long table. So you can leverage if there is like a bridge of the same length between the two of them. You can encode that as one long run. You don't have to, though. And so here we might notice I have a run of actually more than 138. So the maximum number of things I can encode with symbol 18 of zeros is 138. because the length of the run minus 11 is 127, which is the largest 7-bit value I have. So if I want to encode a run of more than 138 zeros, I am allowed to use symbol 18 twice. That's perfectly valid, and so I do that. You might notice that if I do that, I might end up with symbol 18 occurring a lot, and that's one reason why that it's useful that I'm using a prefix code so that I can make sure if symbol 18 occurs a lot or not a lot, that its encoding eventually reflects the number of times it actually occurs. It's a short encoding if it's frequent, it's a long encoding if it isn't. And so if symbol 10, for example, appears only once, it gets a nice long encoding. So the CL code lengths are limited to 7, so this should just say limited to 7, not 7 bits. I can, of course, then store each CL code length in 3 bits. So just like before, because we have these limits on the number of bits that we can use to store the length, we have a limit on the actual length of the code, and that means that even though there are 18 CL code or 19 CL code symbols, which means the Huffman coding could put some of them at depth 18 or something, we have to make sure that before we use the code, the depths are at most 7. Okay, so how do we store this? If I give you this set of lengths, you can use the standard algorithm to to figure out what code I used and then to decode this sequence that I encoded. Okay, but how do I give you the links? Okay, we're actually already trying this. We define a CL code. No, we don't have to do that, fortunately. What we do is we take this code table, which is now a set of 19 values, each of which fits in 3 bits, and we encode that into the block header as a bunch of 3-bit values. And that's it. And we had to boil it down to this because, okay, 3-bit links aren't that bad. But if our links can be at most 15, then that's 4-bit links, and there are hundreds of them, so we don't have that luxury. Here, though, we only have 19 symbols. We can store 19 3-bit values if we need to. So just because we're still talking about block type 2. I convert my input data to a bunch of LL and distant symbols like in block type 1. I then create prefix codes for the LL symbols on the one hand and the distant symbols on the other. I then make a code length table for each one of them. So I compute the lengths of each encoding. And then I encode that with my CL symbols and their offsets. I look at the CL symbols, 0 through 18, and I compute a prefix code for them. And then I use that prefix code to encode this stream of CL symbols, not the offsets, just the CL symbols. And then I've now actually been able, as of here, I now have finally stored into my bitstream the code length tables for my LL and distance codes. So finally, I can encode the block data. The block header includes a bunch of other options that allow us to truncate the length of tables if they contain zeros at the end. So, for example, it points this out. If my LL code is a bunch of stuff, it ends here, and here's symbol 256. We know it always appears once. And here's symbol 257, it appears 3 times, but everything else appears 0 times. I am allowed to indicate in the header that I'm only going to store the entries up to here, and that all the other entries should be assumed to be 0. So I don't even need to encode this run of zeros with the CL code. I can, but I don't have to do that. And so, finally, here we are. It's been an hour and a half, and we're finally ready to talk about the header for block type 2. So the header starts with the isLast. Remember that? I seem to remember that meant something an hour ago. Then the block type, which is the number 2. Rule number 1 applies. And then these 3 things. So hlit is the number of LL code entries that you've chosen to encode. So I just mentioned that you can choose to only encode, here's index 257. If I'm only encoding up to and including index 257, I'm only encoding 258 entries. So what I'll do is I'll set hlit to be the number of total codes present, in that case it was 258, minus 257. So it's a 5-bit number, and it can't be less than 0. And it turns out that means you have to always encode at least the first 257 symbols, symbols 0 through 256. hlit can't be set to anything less than 0. There's wonderful logic in that, because if you think about it, I think that they're going to make it a thought question. That's too bad. I'm going to give it away. I can't help myself. We know that every block contains an end of block marker, symbol 256. because of that, we know that there will not be a run of zeros that goes back before symbol 256. There will always be at least a 1, or definitely a 1, or some length in symbol 256. So we can't have hlit be less than that because it'll never happen. But we could omit the entire length portion of the code table if it's all 0 lengths. All of the symbols 257 to 285. So if we set hlit to be 31, then we're encoding every possible symbol. But if we set hlit to be 1, we're only encoding 258 possible symbols. So it's pointing this out, and that allows you to just not worry about them. You can still put them in there, but if you use this, you can just avoid having them in there and save some space that way. Hdist, similarly, we know the distance code table. If you never use back references, you may not have any distance codes. But if you only use short distances, so codes, 1 through 5, you can avoid having to write the rest of the table by setting the hdist parameter to something. So it's going to be the total number of distance codes you choose to represent minus 1. So you actually are required to always have at least one distance code written. If you never use, distance code length. If you never use any distance symbols, you can have the single code length you write be a length of 0, but you always have to write at least one entry for the distance code length table. And then there's also this issue of the same thing can happen to the CL code. There might be certain CL code symbols that never appear. So there are 19 total symbols, and for a variety of reasons, it turns out you pretty much always need at least 4 of them. And so you can tell how many, you can, in the header, indicate how many more you want to include. So if you want to include all 19 of them, you would set hclen to be 15. If you only want to include 18 of them, you'd set it to 14, or 17 of them, you'd set it to 13. So it's just set to the number of CL code entries you have decided to encode minus 4. Oh, actually, and this should probably be like that. So the number of links that you end up seeing is hclen plus 4 times 3 bits. So, okay, fine. We've written the header. We've found different ways of truncating the tables. We've been through this exhausting discussion of how to encode the original input into a stream of length and literal symbols and distance symbols, then to encode the code tables for that into CL symbols. At some point here, we're going to run out of breath. We're almost at the top of the mountain, aren't we? Well, yeah, but you know the way that this works. You watch the movie about climbing Everest. There's always going to be something happening in Act 3. So here's what we do. We know already we're going to store our code length, our CL code length table. That's going to be this thing. It's coming up next. And just because we obviously can't get this far without adding insult to injury, guess what happens? Well, we're going to write the table as a bunch of 3-bit values. There's the table. It's a bunch of 3-bit values. That seems easy enough. Why can't I do that? Well, the table gets stored in this order. We first store the length of code 16. Then we store the length of code 17. Then code 18. Then for some reason 0. And then we store number 8. So for some reason, we store the elements of the table in this completely bizarre ordering that the RFC doesn't really give any explanation for. It just says store them like this. I looked at this and I had no idea what was going on when I saw this. I thought they're just screwing around. There's no way they really mean this. Why would they do this to me at this point? After all this time. Okay, but they did. And you have to do it this way. So first, we take our code length table and permute the lengths so that the symbols come in this order. Symbol 16, symbol 17, symbol 18, ending in symbol 15. And then so right before that, symbol 1. If you notice that, let's say, these 3 lengths are 0, you can cut it off and set hclen to not write these at all, just like with the LL and the distance tables. But you could write all 19, but you have to write them in this weird ordering. I'm going to come back to the slide once I've shown off how this actually works. So here's my code length table, the rational looking one. I have to rearrange the columns to be in the funny order that I'm using, so I end up with this. Now you'll notice, because of the way the CL code was defined, hclen won't help me here. So hclen is that parameter that lets me avoid writing the last few entries if they're all zeros, but the last entry is not a 0, so I can't use it. But when I've rearranged it, hey, look at all those zeros. Well, that's nice. I can set hclen to only write the first 16 values. Oh, that might be a typo. It probably should say that I'm writing the first 14 values instead. So I'll correct that when I post it. So I'd say I would like to set, in this case, hclen equals 10 to only write 14 CL length values instead of 19 because the last 5 entries of my table are 0. So it turns out the reason that the encoding order is so bizarre is that if we rearrange them into this order, we tend to put, on average, the code links that are least common and are most likely to be 0, the symbols that are least likely to be used, we tend to put them at the end. So think about this. Okay, so CL symbol 1, which is the second to last thing. CL symbol 15, what do those mean? Well, symbol 1 is used when you're encoding a code length of 1 in your LL or distance code table. 15 is used when you're encoding a code length of 15. But think about it. When you're encoding a large piece of data, how likely is it really that something ends up with an encoding that's 1 bit long? That's not very likely. And also, if all goes well, how likely is it you end up with an encoding that's the maximum 15 bits long? Also not very likely. And so what this is saying is it's basically trying to encapsulate the fact that really extreme lengths, 1 or 15, are pretty uncommon. And therefore, they're the ones most likely to never appear. And if we rearrange them, maybe we can cut something off. We can save a few bits. And keep that in mind. All of these weird somersaults we're doing are to save 1 bit here or 1 bit there. So in any case, whether we think this ordering makes sense or we like it or not, we have to encode things in this order. We take our length table, we encode the length for each symbol following that order of symbols. We've seen a lot of weird tables today, the table of length and distance symbols, and the table, this funny ordering. If you go to the gzstat source code, you can actually copy and paste like array versions of these instead of having to type them in yourself out of the slides or out of the RFC. So after my hclen field, I am encoding this number of bits, so 3 times hclen plus 4 code lengths. The first hclen plus 4 elements of this representation here, starting at this end and going into whenever hclen plus 4 is. And of course, those are numbers. They're code lengths, they are numbers. Rule number 1 applies. And then I take, I have my CL code length stored. I then store that bit stream that results, it's way back. I store that bit stream that results from using my CL code and those offsets to encode the length tables. I store that entire bit stream. And then finally, after that, I store the encoded bit stream for the blocks data. So we might remember long ago, we had data that we were going to compress. I'm at this point wondering what compression even is. So we had this data, we want to compress it. We've finally gotten to the point where we can actually begin storing that data as opposed to metadata to describe the codes that we're using. So using our custom LL and distance codes, we dump out that bit stream computed using the LZSS length and distance symbols and literals and those codes here. And then the end, and somewhere in that stream is the end of block marker, and that's the end of the block. There's a lot going on. So I want to walk through a complete example of generating a block in type 2. And I realized in the middle of this odyssey of this lecture, there's one slide missing here. At the very end, I actually want to have a slide showing the hex value of each thing so we can see that bit encoding to sort of bookend the whole thing. So I have this. And here's my original data. We can see it's got quite a few recurring patterns, ABCD, ABCD, and then the entire first word appears again. And the goal there is to see as diverse a set of back references as we can get in a small example. So I add my end of block marker, and then I end up with this, with LZSS. So I've got my some literals, I've got some length distance pairs, and I've got my end of block marker. Now, we should note, if you actually try to encode this input with gzip, it will generate a block of type 1. Because it'll notice it's not worth it. You're never going to get enough of an advantage from the block 2 mechanics to overcome the huge overhead of storing all that stuff. So it'll probably use block type 1. There are cases where even block type 0 is better. It's actually better than block type 1 in certain cases. Something, again, I think I mentioned this a million years ago, but to put a bookmark in for a midterm to think about. Okay, so here is my ultimate LZSS stream with my back references. So I take that and I prepare, I don't yet have an LL code or a distance code, but I convert it into my LL and distance symbols. So I can see symbol 65, it appears Oh, I guess just once. There's symbol 258, it appears once. There's symbol 263, it appears once. In fact, actually, it looks like every LL symbol that appears only appears once. It's hard to contrive examples where you get more than that. I noticed there's my distance symbol number 4, there's my distance symbol number 6, and there's some offsets in there. So I convert it this far. I converted this vector of LL and distance symbols, and then I go through and I compute the frequency of each symbol. Some symbols, like, I don't know, the letter F, never occur. Some symbols occur once. I don't think anything occurs twice. So I compute the frequency of the symbols in both alphabets, the LL and distance alphabets, and I compute these frequency tables. So they're sorry that they're a bit crammed in there. We'll notice all these frequencies are just one. And then only two distances ever actually appear, distance symbols 4 and 6. And we might notice, hey, wait a minute. So if there's only two symbols and they both have the same frequency, my prefix code tree will probably just look like this. I'll have here's symbol 4 and here's symbol 6. Great. If I used block type 1, I wouldn't get that advantage. So I'm actually able to define an extremely short distance code. So there are my frequencies. I can go compute code lengths from that. So I run that through Huffman coding or something. We'll notice that even though all the frequencies are equal, some things get length 4, some things get length 3. That's just tough luck. I mean, that's because there aren't enough. We can't give everything. There are more than 8 things that I have to encode, so I can't give everything length 3. These, of course, have length 1, like I suggested on my previous slide. So there are my code length tables. So from the code length tables, I can actually compute the codes. There they are. So I run these through the standard algorithm, and I get these codes. So the distance codes I pretty much are what I expected. Great. I have enough information now to actually encode the data, but I'm not ready to do that yet. Before I put any of my encoded data in my block, I need to first encode the block header. And so now here we are going back down the rabbit hole with that. Okay, so the first thing I notice is I don't have to encode every entry of these tables. So I have the option of cutting off the tables before a run of zeros at the end. So I can cut off the LL table here, and in this case, I only want to encode up to symbol 263. So I set hlit to be 7, because I have to, hlit is the size I want. So I want 264 symbols, 0 to 263, minus 257. Same thing, I'm going to set hdist to 6. So I'm only encoding the first bit. I'm saving a bit of space, not encoding the end of the LL code table. And I'm saving a pretty decent amount of space by avoiding encoding almost 23 things from the distance code table. Okay, so now I take those sequences, the parts of the table that I am encoding, and I encode them with the CL symbols. So I end up with this. Here is so remember that the last entry of my LL table is now 3 because I don't even worry about this. So I encode the LL table with my CL symbols. There they are. It's these symbols here. And whoops, not that one. And we'll notice that here there actually is a pretty decent distinction of frequencies. I see the symbol 3 quite a few times. I see the symbol 4 twice. I see a decent number of 18s as well. I only see, I think, one occurrence of the symbol 16. And one occurrence of the CL symbol 0. So here's a sort of rare case of this. We normally see like runs of zeros getting encoded with the special symbols. Here's just a 0 sitting by itself, just one of them. So we can't encode that as a run, so we have to encode that as a literal 0 value. There's the one for the distance table. It's 4 zeros, then this length 1, then a length 0, then a length 1. The rest of the table gets omitted because we set hdist. Okay, so I have these two things, these two sequences of CL symbols. Using these sequences, I can now compute the frequency of each CL symbol. And from that, I can use Huffman coding and compute the code lengths. And then from that, I think it's better to go backwards. From the code lengths, I go backwards and I compute my table of CL codes. So I have this, I run it through the standard algorithm, I get this sequence of codes. So we'll notice, for example, that 0 didn't appear as often as 3, so quite predictably 0 got a longer encoding than 3 did. Interestingly, 0 did occur the same number of times as 1, but just bad luck, it turns out that 0 ended up with a longer encoding than 1. So I have a prefix code for my CL symbols, and now I store the prefix code in the header of the file. So I set hclen to be 14 because I noticed that once I permute the table into encoding order, I have a 0 at the end, so I don't have to encode all 19 things. I can suffice to encode only 18 things. So I set hclen to be 14 because hclen plus 4 then equals 18. Then into my block I add my, so I guess then I can do my encoding. So I then know the encoding for each CL symbol, and I generate it from the code table I had a couple slides ago. There it is. And I do that for the distance code as well. Sorry that it's not very big on the slide. Okay. So I now have these encoded sequences. I've got this one, which is the code length tables for LL and distance. I also have this one that I'm holding on to, which is the actual encoded data, which is surprisingly small if you think about it. It's very little of what I end up writing is the encoded data because of all the overhead I need. So I have everything, and now I just have to put it together. So I'm going to remember this sequence, 0, 1, 1, 0, 1, 0, 1, 0, 0, and we'll see it in a few slides. So I write isLast is 1. I'm only going to write one block to my file. Block type is block type 2. We notice that got written least significant bit first because it's rule number 1 applies. And then I write out my numerical parameters, hlit, hdist, and hclen. The first two are in 5 bits. hclen is in 4 bits. And then I write my code length table in the funny order. And I end on code length 1 because I didn't have to write the last thing in the table because it was a 0 and I set hclen. So I write that in the bizarre order that it requires. And remember, this is the code length for symbol 1 is 3, but it was a number, so I wrote it least significant bit first. And then I write that bit stream, that would be this bit stream. I write this entire bit stream out. That's the LL code table. And then I'm going to write this entire bit stream out. So if we follow it, there's the LL code table. There's the distance code table. And now finally, at long last, I am ready to fold in that encoded representation of my actual data. There it is. And that's the bit stream. That is the encoded block. Now, you stare at that and you say, wow, that's an hour and 50 minutes of my life I'm not going to get back. And also, how do I know this is correct? We've just been talking about bits so long, I don't know what bits are anymore. How do I know this is actually a correct encoding? If there's an error in this and I spend days and days on an assignment, I don't want to find out I was working from a bad source. Well, don't you worry. I've spent enough time having to debug single bit errors in this that I can stand by my words. At least you've seen all the typos. Those were all irrelevant to function. I guarantee you this is actually what this block looks like. And I have posted a file to Connex that contains this exact bit stream, bit for bit, that decodes to the data we saw at the beginning, 20 slides ago at the beginning of this example. So this is the correct encoding. It is not the only correct encoding. There are lots, and you should have seen, look at all those variables we had to deal with. You could have chosen not to generate a back reference. You could have chosen to use a different CL encoding. You could have decided not to worry about hdist and just set it to all to 31 or hlit or something like that. There's so many places to make decisions, so many places where you as the implementer have to decide, do I want to worry about this and save a couple of bits or not? It's very important to consider, like I did at the beginning, that if I fed this into gzip, it would use block type 1, and that would take 94 bits. That is half as many. And if you notice, the actual data wasn't 94 bits. I just had to spend tons and tons of bits describing the codes that I'm using, and of course describing the code that I use to describe the codes. So of course we don't want to use block type 2 for tiny inputs. And if you include logic to that effect in your assignment 2 submission, you can get some marks for that. So logic to not only use block type 1 for small inputs, but also even on a big input. There are times when it might be useful to take a break and switch to block type 1 or block type 0 because for some reason block type 2 won't help you on whatever data you're working on. Gzip compressors usually do contain some logic to try and choose block types. All 3 block types exist for a reason. There are times it's better to store data uncompressed, and there are times it's better to use block type 1, even on large inputs or small inputs or whatever. So, obviously, there are those magic words again. Good exam question. I'm sitting here thinking, oh, wow, this is a course and I have to give exams and words have no meaning to me at this point. If I give you an input, you should be prepared to think about and discuss reasons why a certain block type might be more or less of an advantage. Not necessarily what the best one is, although that's That's an easy question. Like that's the obvious one. But also, here's an input. Why is block type 1 better than block type 0 here? Even if the best type is block type 2, who knows? Even if the best type is block type 0, give an advantage of using block type 1 on this particular input. Okay, so there's a lot there. We talked about a lot of things. We've seen that the real issue we have here is panicking over the number of variables we suddenly have control over. There are so many things our compressor can choose to do or choose not to do. There are ways that it can increase speed by not worrying about something or worrying about something differently, and ways it can increase compression by doing a more thorough search or a less thorough search. And it's a trade-off we have to achieve. On the assignment, you won't be marked if your code takes hours and hours to run, because we have no way of validating it if that's the case. But you also want to achieve high compression. And it turns out you can write a gzip compressor, theoretically, that's more powerful and maybe faster, but gives better performance than the actual gzip compressor. It doesn't necessarily use all of the options it has at its disposal. So, after all this time, let's talk about some of the options we have. So, if you want to optimize compression, what can you do? Well, you can think about, how do I split the input into blocks? If I'm feeding you 100 megabytes of data, how do you decide how much goes into a block? Maybe you can't fit all 100 megabytes into a block because, as you've noticed, if you want to have a block of a given size, you have to save up the data before you can write it out, because you have to have all the data before you can compute the prefix code. If you have to split it up, where's a good place to do that? Should you split it into 100 1 megabyte chunks? Should you split it into a few chunks of 100K and a few of 10 megabytes? Because block types 1 and 2 have no limit, you have quite a bit of leeway there. And it could be that if the data has certain patterns, maybe it's better to alternate. It might also be better to use more blocks, because every time you define a block of type 2, you can define a new prefix code. And maybe as the data changes, there's a place where a different prefix code would really improve compression. And you can see why that's a tough problem to solve, because you might have to try different possibilities before you know which one is better. And then there is, when do you use block type 1 versus block type 2? And a rule of thumb is block type 1's fixed code is sort of middle of the road. It doesn't really give you that much compression for the most part. It can help if you have LZSS to give you some compression, but it's better for smaller blocks and for blocks where there's not many patterns that give you a more nuanced compression tree, where pretty much everything's at the same level. Block type 1 might save you enough overhead there to be an advantage. When do you encode a back reference? This is an ugly one. So it's not only, okay, I get it, back references that are 30,000 characters before are going to require more bits than ones that are 10 characters earlier. Or maybe in some cases, the back reference takes so many bits to encode, I better encoding literals. If it's a back reference of length 3, 30,000 characters in the past, maybe I'm better encoding literals. It's more complicated than that, because it might turn out, as we saw, we store back references using these length symbols. And the more you use a length symbol, the shorter its encoding gets. Which means if you choose to not use back references, the back references become less efficient. If you choose to use more back references, even weird ones, like ones that are 30,000 characters in the past, they might end up saving bits. And so it becomes a funny Nash equilibrium in a sense, where if you're able to find 10 back references of a certain long distance, maybe they become more efficient. But if you only have 5 of them, it's better to use literals. That's a really, really ugly optimization problem. And if you make any progress on a problem like that, even as a toy example on the assignment, you can get some marks out of that. There's also this sort of related one of when to choose back references. So suppose you have a string where, I'm looking at these characters here. This is my look ahead. And then back in the past, so this is A, B. And then back in the past somewhere I've got A, B. And then back in the past even further, I also have A, B. And then even further away, I've got another A, B. And, whatever else. I've got multiple places I can choose to go for my back reference. We could say, well, okay, the shorter the distance, the shorter the encoding, right? Well, maybe, hopefully, maybe not. Maybe it's the case that you've got lots of other back references of this exact distance, or using the same distance symbol. If that's the case, maybe because of the weird way that this encoding works, the distance symbol actually will have a shorter encoding. Maybe the best back reference isn't necessarily even the one that gives you the longest match. Maybe choosing one from a specific place in your string gives you some weird weird out-of-band advantage because of the weird interference between LZSS and the prefix coding scheme. That's why this is a big deal. It's not just there are lots of options. It's what you choose now affects how feasible what you choose next is, but strangely, what you choose next affects how feasible what you chose now was. That's a big deal. Of course, it's one that gzip doesn't solve. Arguably, if gzip was written today, if we took into account that we've got lots of extra processing power lying around, we could take a crack at these problems. You'll notice, though, that more modern schemes don't try that. They instead just say, use a larger sliding window. That's easy. That's adjusting constants. So this slide talks about this weird, creepy feedback loop that exists. The more back references you use of a specific type, the more efficient they get. It's not as simple as saying it's further back in time and therefore it's less efficient. And so I already talked about that. So what about this other option of speed? So the assignment covers both of these things. You get to choose how many back references to generate and whether to look for them at all. You could decide for a specific input or a specific part of your input to just stop generating back references. You could also say, hey, I found a back reference of, I don't know, length 10. I'm not going to look much longer. Maybe there's one of length 100, but I'm not going to look much longer because it's not likely I'll find it. You could also use a sort of decaying search strategy where the further back you go or the more thorough you are, the less you actually check. Maybe you check every index going back for 100 characters and then every second index or something, which means maybe you find what you want, maybe you choose random indices, but there are ways where you could still get back references without necessarily having to slog through huge amounts of data. If you want to optimize for speed, you might notice block type 2 has a lot of overhead. It's not actually that much in a real computational sense. It's just a lot of cognitive overhead. But there are times in which maybe block type 2, you might notice for some reason that you're not going to get much advantage out of using it, so you just defer to block type 0 or block type 1. And then there's also the question of, we've seen all the weird options we can employ in block type 2. So all the ways we can optimize our code, there are cases where maybe it's easier to short circuit and do something simple. Still use block type 2, but do something very simple because it turns out that maybe we'll not get much benefit from doing everything all the way through except wasting time. And that's the key thing. And you'll notice the gzip encoder actually does something like that. It cuts a surprising number of the corners that we've seen. It doesn't consider this feedback loop. It actually also, you'll see in my other video, it encodes lots and lots of blocks. It doesn't save up as much stuff for a block as you'd expect it to. And yet it's still incredibly fast and achieves really good compression because what it does, it chooses to discard certain information in its search for back references and how it encodes things. But what it keeps around is what it needs the most, and it does it really well. That's what you'd expect. You can't really expect to compete with gzip. They've had years of a head start, and they've had huge amounts of data to work with. But keep that in mind. It isn't perfect, and it isn't even exploiting, despite being the reference implementation of Deflate. It isn't even exploiting all of the different options that Deflate gives it. All right, so I'm just about to hit the 2-hour mark. I figured this was going to happen eventually. If I end the video in the next 30 seconds, I won't hit it here. So there's another time to set that record. It's not going to be today. So I'm going to go I'm going to go rehydrate. Maybe this is a good time to either start on your assignment or just like me, you can go, I don't know, collapse on the sofa somewhere or something.